Okay, so let's continue to 2B lecture. This is the part 1, in which I basically discuss the Gauss's law. But before Gauss's law, okay, we let's look at the field lines, a concept which is uh, a cartoon, but it's a very helpful cartoon or a cognitive device. So the field lines can be for a negative charge, for example, it will terminates on for a positive charge. So this is a two-dimensional representation of a three-dimensional thing, but it's still very helpful. Okay, so if I have two plus charges, you can see that they repel each other. There is a tension, all right, and you can recognize this. This is 1 plus and this minus. Okay, so though this is a cartoon, this is indeed helpful, and during the course, I will actually ask you to plot many such field lines as we go along. Okay, even in the exam. What are the features of the field lines? Well, let me illustrate the way they terminate. Okay, there are features you will understand as we go along. Okay, but then there's you can see that there's some tension. Okay, along they're not lying loose, they're taut. Okay, as if you can plug the strings. Okay, so putting together its ends, trying to. There is repulsion, of course, just as we saw. Okay, the two lines will as if they would repel. And what is the direction? Direction is the tangent. Okay, at any point, the direction is the tangent. And how many lines are you drawing? Typically to show the intensity. Okay, the proportion of the lines per unit area, per unit length are is an indicator of the intensity. Okay, so of course there are two important properties of these lines. There is no intersection possible. Why? Because same point can't have two directions. Okay, and there's no closed loop possible, because if it is closed loop, which means at some point there is both plus and minus, which doesn't make sense here. Okay, there are techniques which will help you do this once you go to potential. Okay, because equipotential lines also help drawing these field lines. Okay, but for the moment it's okay. Now let me go to flux. The flux, we know the electric flux phi E. Let me write it down. The electric flux phi E. Okay. Of course, we have done already flux in the first chapter. And this is over the whole surface S. If the electric field is E, then dot dA. Now let's charge, and of course, if let's say if uh, there is a surface, some arbitrary surface, okay, and I have um, field lines, let's say, straddling this surface like that, okay, but the normal to the surface is, let's say, n. All right, so if this I consider to be dA, if I consider this to be a dA, then in dA is normal to the plane and the area dA. Okay, so if this angle is alpha, then I could call it also E cos alpha as E dot dA. So we know this is d phi E, small amount of flux going through an area d phi E. So, and the total flux, of course, through the surface would be that. So this is something that we have already done. Let me remind you that we had actually done. Um, we have actually done. You remember the disk and a sigma charge disk and a point under Z. And what was the field like on the Z axis? We knew that Ez was was sigma by 2 epsilon naught 1 minus Z by root over Z square plus R square, taking this to be an R. Okay, and then the K. Now let me reverse the problem. Okay, suppose I have a same disk of radius R and I have a point charge Q here. So then I ask, what is the flux? Point charge Q here. What is the flux going through the disk? Okay. There is this is a dA missing here. All right. So you could actually work this out. And what you will find is, let me tell you the answer. The flux phi going to the disk, phi E going to the disk, is Q by 2 epsilon naught 1 minus Z by root over Z square plus R square. Why is it look so similar? Can be justified on the basis of the solid angle subtended, but in this course we don't use the concept of solid angle so much. But you can exactly work out the integral by taking a small area and integrating it. All right. Okay, so basically the flux, to summarize, is that it is the normal component of the field going through any surface. Okay, so this whole thing is the normal component of the field going through a small area dA, and integrated over all S will give you the flux. Okay, so let's start Gauss's law, and I'll take the first simplest possible proof, that is using superposition. Let's start with a point charge Q at origin, point charge Q at origin, and a spherical surface enclosing it of radius r. Spherical surface, radius r. Let me draw that. Let that be okay. And I have a point charge somewhere at the center. This is radius r. Now I can easily write down the E for the whole surface, E dot dA, and that will be, of course, we know the 1 by 4 pi epsilon naught. Okay, we know this is Q by R square, the field, and the direction is R hot. Then it is R square sine theta d theta d phi dr. All right, if this is point Q. Now this, of course, okay, R and R So that gives you, and this goes 4 pi epsilon naught. I don't have to this is q by epsilon naught. What is the most important fact here is that this r square and this r square cancels. That's how exactly Gauss's law works. All right. So if I have the field lines going like that, we have seen the field lines. So if the field lines are like that, okay. Now, so they cross, and the way what this means is the way the area is increasing, that is r square, and the field is also increasing q by r square, and that is why they cross out. So the inverse square law is extremely important for this to work out. Now, does this depend on the choice of the, suppose I had another surface, okay? Let's say I had another surface instead of this, okay, and some arbitrary surface, okay. The same lines still go through. So it really does not matter which surface that which surface, closed surface that I choose to, as long as it's closed surface, okay. So closed surface of arbitrary shape, this is true. Except that it is useful only when arbitrary shape, okay. Then once I've gotten this result for one charge, I can always work out for a bunch of qi. So let's say a bunch of qi, and then that would be E, let's say, let me write it down as I is equal to 1 to n E I this. This is from what? This is from the principle of superposition. This is the crucial argument that is, this principle of superposition comes from where? Comes from the Coulomb's law. Basically, we know that Coulomb's law. And then now, if I write down E dot dA, then I can take this to be I is equal to 1 to n. Let's say then the field due to each, we know that is, so the flux due to each qi, okay. So I can sum it up, and this is nothing now but I is equal to 1 to n. We know for each of them is qi by epsilon naught, okay, which can be written as q enclosed divided by epsilon naught, okay. So this is true for any surface. Since it is true for any surface, I would say that this is EDA is Q enclosed by epsilon naught. Okay, so this is the statement of the integral Gauss's law that we already know. Let me suppose it was something like, suppose it was a volume which is, the charge is here, okay. and this is the volume, but charge is outside. Okay, so then what is the so there will be of course and so on and so forth. Okay, but the total flux going through, the total phi e would be 0 because it's not Q enclosed. So whichever lines are passing through here, okay, also are going out. There are lines passing, but passing number of lines going in, also number of lines going out, and the total phi e. So if it is not, if there is no, for any closed surface, if there are no charges, then E dot EDI is 0 is a normal corollary. Okay, so this is the integral form of the Gauss's law that you are sort of familiar with. Okay, let me, the important, oh, there is a, I noticed a terrible mistake. This of course should not be there because I think I wrote it off. Galti se mistake. I think I can afford to do that. You cannot. All right. So this is important part is the differential Gauss's law. Okay, which I'll use the divergence theorem to obtain. Okay, so this is simple because we have done the vector calculus. Once vector calculus is very simple because over a closed surface, if I now say E dot dA, then I can always write down as a some volume V, grad of E is completely general. Okay, and what am I using? Of course, divergence theorem. Except that now I have written it down specifically for the electric field E. Okay, and at the same time, I also recognize that what is Q enclosed? Q enclosed in terms of this is, let's say, rho, okay, is given as in some volume, and this is d tau. Okay, and hence I can see that the volume V, so this is d tau. Okay, and I write down now this. Okay, this is rho by epsilon naught d tau. Simple. Okay, this is again true for any volume of choice which completely encloses it arbitrarily, and hence this must be true. Hence, okay, it's grad E, the integrand must be equal, since this is true for any. So that is this is the integrand. Okay, and hence I would be able to write down the differential form, and this is the most important. Okay, so this is true for any volume. So this is straightforward on application of divergence theorem. Let me get the same result from the integral form of Coulomb's law. Okay, so what is the integral form of Coulomb's law? We have already done that. Let me write it down. That is E R. So this is 1 by 4 pi epsilon naught R by R square rho, which is only in the prime coordinates, and d tau prime. Okay, I remember all the time that this is R is the position of the field point minus the position of the source point. Now I can include this to all space. Why is that? Because I don't lose anything. If there is some enclosed space, I can always include in the all space. Okay, and so I can now work out the divergence of E, and that is, I will take 1 by 4 pi epsilon naught divergence of r hat by r square rho r prime d tau prime. Now this is something that we already have done, this quantity in our last week's lecture. This is, so what is that? We know that this r hat by r divergence of inverse square is 4 pi, the delta function, three-dimensional delta function r, correct? Okay, I'm just in. So since we have done that, now our life is quite easy, and hence divergence of E is 1 by 4 pi epsilon naught. This is 4 pi del, I can write it down better, the actual r minus r prime, that is rho r prime d tau prime. Okay, and this will be, you'll simply pick up the, since this is a delta function, the integral will simply pick up the value of the charge, the function, the value of the function at this. Okay, and so that is nothing but rho of r by epsilon naught. Of course, this and this cancels, and that simply picks up that. And hence, I now know the most important of the same result, okay, that is, this is from the Coulomb's law, that is divergence of electric field is rho by epsilon naught. So this is another route to obtain the Gauss's law in differential form. And hence this appears that the Coulomb's law and Gauss's law are totally equivalent of each other. We can work out the inverse differential integral also, that is from differential to integral, and that is straightforward, okay, because we know this. So that is knowing rho r by epsilon naught, okay, gives rise to, I can integrate on both sides for some volume V, divergence of E d tau, okay, and that would be for the whole the surface enclosing E dot dA, and hence this will be 1 by epsilon naught rho d tau, and that is equal to Q enclosed by epsilon naught. So which way you like, okay, the two are equivalent, and there you can get, so this is the inverse, that is given the differential law, I can get the integral Gauss's law. All right, so let me make a few remarks on Gauss's law, okay. This is, why did it work? Because the force is central, okay. This is one of the, it has to be central force. Not only that, it has to be inverse square law, 1 by r square. So it has to be a force which is inverse square law. And that is what the cancellation work did, remember? Okay, inverse square law. And superposition must work. So superposition must work. This is a very general, this is very powerful, but practically useful in highly symmetric cases and depends on the choice of the Gaussian surface. And this choice of Gaussian surfaces helps in symmetric cases. However, I would say that is more powerful than Coulomb's in one sense at least. Okay, that is, I can give you an advanced alert. Okay, that this remains valid even if source is moving. Though we are talking at the moment here of electrostatics when all the charges are static, but even when it's moving, Coulomb's law is not valid. Okay, but Gauss's law can still be valid. Okay, so but that we'll discuss if I have time to take up relativity a little bit towards later part of the course, then we can discuss that. Let me take up standard examples, applications of Gauss's law. I know that you are familiar with, but but I will go through them in any case quickly, pointing out some of the things that requires revision, or if you have not done them before very well, then it's important to sit down and do these standard examples and write them out, making sure that you understand each part of the argument. Okay, that's the first thing that I would take up is the standard a long uniformly charged wire. All right, so this is the long charged wire, and of course, since this is infinity, okay, there is no way but the field cannot have any component in that direction because it is going to infinity, and hence it has to be confined to the xy plane or must be perpendicular to the, okay, and hence I choose the Gaussian surface to be cylindrical. Clearly it is a cylindrical symmetry of a arbitrary length L, all right, and then argue that the E on the curved Gaussian surface is same everywhere at the same R because of the symmetry. All right, so it's same, and which is the direction it can point? It can point only in S hat direction. S hat direction is the in this direction. So there is and there will be no flux to the flat surfaces. All right, so if you do that, then the E dot dA over the surface belongs to the curved surface. Curved surface, the field is in S hat direction, and this is the surface normals. And surface normal here happens to be also the S hat. Okay, and of course flat top, there is no field going in that direction. Okay, and both the flat bottom and both contribute nothing. So ES, this is S dot S, and what is the surface area of the cylinder? 2 pi SL. Okay, L is arbitrary length, and so and that must be equal to the Q enclosed. Q enclosed is clearly lambda into L by epsilon naught, and hence the standard result of lambda by 2 pi epsilon naught. In most books is written in terms of R, but in Griffiths we are following cylindrical symmetry to be S, and this is S hat. All right, and going to infinity. We had gotten the same result using Coulomb's law for a short segment and then extending the result to infinity. Okay, in Gauss's law, you cannot obtain for the short segment because you would not have you will not be able to choose a proper Gaussian surface where you could make the convenient the integral of convenience. All right, so note that the E falls off as 1 by S, okay, which is slower than the point charge. The point charge goes as 1 by R square. But there is a difference in meaning of S, and S is only in root over x square plus y square. But R here means root over x square plus y square plus z square. Let me take up the next standard example, which I'm sure you also know already, but let's go through it for its importance. An infinite plane surface charge with sigma. Okay, so we can choose a pillbox, okay, which is sort of rectangular or cylindrical, such that only these two flat surfaces contribute with area A, and we know that is only will be in the k direction. If I say this is my k direction, all right, um, and then by symmetry, Ez is also minus of minus E minus Z. Okay, so the total surface integral, the sides, I can always reduce this to 0 almost. Okay, and anyway, there is no contribution from the field because of the symmetry going through, so it's only Ez A minus E minus ZA, and the total is 2EZA because of this, and that's total charge that is included is sigma A by epsilon naught. Okay, and so sigma by 2 epsilon naught k z greater than 0 and minus k z less than 0. Of course, it can always be written in terms of z by mod z. Okay, so as a generality, you can always write down this as E equal to sigma by 2 epsilon naught z by mod z k. Okay, uh, so but there are two things to note. Okay, which is that is independent of distance from the plane. As I go, okay, that something which with point charge we started with 1 by r square, with line charge it became 1 by s, and now it's because it's infinity in 2 dimensions. As you keep going away from it, okay, you come into your view the charge that you see from your the solid angle subtended, you see more and more charges, and that exactly compensate such that it remains a constant. There is no distance independence. And also note that the E above and E below, if you go, okay, then there is sigma by epsilon naught. There is a discontinuity. This is something, a general feature. We will talk more about it. But anytime you have a surface charge of sigma, then the electric field's normal component will go through a discontinuity with sigma by epsilon naught. There's the important case, of course, is if it is single, then this both ways. Okay, but if there are two of them, plus sigma and minus sigma, and this is the z direction, I've just turned it around like a capacitor. So there is no field outside, and inside field is sigma by epsilon naught. This is frequently we'll use it because it's like a capacitor. If I again plot it E as a function of z, then below it is minus sigma by 2 epsilon naught. And if it's the thing is that z is equal to 0, then there is a jump to sigma by 2 epsilon naught, and the total jump is sigma by epsilon naught. If there are 2, then it is 0 here, then jump sigma by epsilon naught, and then jumps down by sigma by epsilon naught. All right, this is important to keep in mind. So this is also important to see that for a point sufficiently close to any arbitrary shape, let's say sigma, a surface charge, close to any surface, if I go close enough, then the surface will appear to be an infinite charge with sigma. And hence it is very widely used charge configuration. So jump, and then as soon as you cross the surface charge, then electric field will give you a discontinuity of sigma by epsilon naught in the normal direction. We will discuss this more about it. Then the other standard case of a uniformly charged sphere of radius r and in volume charge density rho. So of course that you choose a spherical Gaussian surface, okay, for r less than r, and so for okay, and then has only r component from symmetry itself, and so total surface I can now calculate ERR R dr Q enclosed by epsilon naught. So this is E I can take out of the integral. The total area is 4 pi r square. R is the small r, right? This is the small r, okay, and this is the capital R. So, and then ER is simply rho by 3 epsilon naught R, or in vector form, E rho R 3 epsilon. This is extremely important. This has to be on your fingertip. This will be used so often in the course that it ought to be on your fingertip. You can always convert this rho in terms of total charge inside, okay, and re-express this. But what is important is the electric field increases linearly with distance inside. Okay, so this is E, which is inside. Of course, I have already indicated that by saying that R is less than R. The R greater than R is even simpler, because again same thing would work, E 4 pi R square. Now R is greater than R, but the total charge is rho into the total charge 4 pi by 3 R cube, and hence I can write down in terms of rho by 3 epsilon naught, 4 pi cancels, R cube by R square. This will be exactly like as if all the charges are at the center of the sphere. Okay, this is Q and it's an R hat. This is something that we know, and this is extremely important standard case of Gauss's law. Let's see how it works out in terms of its linearly changes here, and then goes as this goes as 1 by r square, like a point charge. Okay, so that's also, and then the surface charge. What is you can note that the E is continuous. Okay, E is continuous at r is equal to r. Okay, but not dE by dr. dE by dr, the slope here is positive, the slope here is negative, but there is no surface discontinuity like we had in case of surface, okay, because there's no surface charge. Okay, there is a continuous continuity, and then it goes to 0. So for a spherical cell, of course, we know that inside E is equal to 0. You can prove it in many different ways, but you can take any shape around any point, any volume, and it will turn out to be 0, and hence it must be 0 inside exactly. Whereas outside, it will look like as if all the charges are in the center, and hence outside it will be, of course, okay, like a point charge. Okay, now these are the standard cases which I went through quickly because I know that you are in some way familiar with it. Let me take up now a case of another new case. A spherical cell is an example. A spherical cell of radius r. So let me draw a spherical cell. A spherical cell of radius. Okay, so let me draw a better circle. So this is a shell, okay, and you have sigma is sigma naught cos theta. Now the question is, can Gauss law be used to obtain E inside? Okay, so this doesn't have the spherical symmetry that we are so used to in Gauss's law. So on the face of it, it looks like it cannot be used. It's an extremely important example, and hence I'll go through it. We can, okay. So this is an example I'm saying is 2b2 with Gauss's law and superposition. We can arrange a superposition. See, the combination of Gauss's law and superposition can also result in not so symmetric. That is, you take symmetric objects and produce such that the resultant is unsymmetric. But since superposition is valid, okay, you separately apply Gauss's law and superpose. That's another strategy. So this is the same strategy that I like to illustrate. Okay, so this step one. So there's two steps I will do that. Okay, in step one, I'll choose what we have just seen. I'll choose a sphere. Okay, and it's a volume charge. It's a total volume charge, and let me say that total volume charge with this is, let's say, positive volume charge. Okay, so this is positive volume charge rho, and so this answer I already know for inside. All right, then I take another let's say another same radius r. Okay, and now this time I have minus rho. Okay, so I have this time it is minus rho. So there is an overlap region. Okay, this also you might have done in your earlier years, but is an important example, and we should do that. So step one. So both are radius r, and this is plus rho, uniformly charged plus rho, and this is uniformly charged minus rho. Let's say the centers are here and centers are here. Okay, slightly displaced, and center A, B. Okay, and now I want to find out what is the electric field in point P given here. Okay, so the answer that we already know that E at the point P, which is inside, okay, would be superposition of the what is for each of these alone. Okay, that we know that for a spherical charge, this is E inside. Okay, rho by 3 epsilon naught for r less than r. All right. So then for this is minus r and plus r, and hence I can write down that this is for the point P, this is rho by 3 epsilon naught. Let's say this is point P, so this is A P. Okay, so this is the point, this is the line AP, and then the other is because of the minus charge will be rho by 3 epsilon naught PB. Okay, because it is minus, so this is PB. All right, so what is the resultant? I can do the vector, so rho by 3 epsilon naught is then AP minus PB, and that is nothing but the vector AB. So rho 3 epsilon naught AB. All right, which is nothing but the vector joining the two centers. Now, what is the field in this region? What does it say? It says that the field is constant. Okay, in the overlap region. So the field is a constant vector. Field is a constant vector. Both magnitude and direction are fixed. Constant vector in the overlap region. And what is the charge in the overlap region? Charge is 0. That's how it is arranged. Okay, so charge density inside charge density is equal to 0. So this is it is, you can, so this is a constant, so uniform lines. So this is one way of getting practically the uniform electric field by overlapping two spherically uniformly polarized with plus and minus. All right. So this is so the and in the region has no charge density. Okay. Now this step. Now I'll take the next step to our original problem. So step 2, in which I will now arrange such that the negative charge and positive charges are displaced. Okay. So this is let's say the positive charge, and the negative charge is displaced slightly from the center. This is the center for positive charge. The negative charge would be slightly, let me draw it carefully. All right. So so then what is the really the charge upstairs? The charge would be just this, the positive charge. Okay. And this is because inside now it has become, okay. So and inside I can say that this is 0. Okay. So no charge is here. So this is a special case of the thing that we already have done. Okay. So if the negative charge is here, then there is this is the D vector pointing from, let's say, positive to negative. Okay. We have just displaced by a small displacement. Okay. So a small displacement along the k direction, small displacement along the z direction, small displace along z direction, and by, let's say, vector d. Okay. Now we know the answer now quite clearly. That is, so that E inside. So E inside would be, we know the already this answer I can take. So rho by 3 epsilon naught AB is nothing but D. Okay. Now this, so which is a constant. Now what is the charge distribution on the surface? Okay. So which means I have the charge, there's a constant which is in direction, and that's the, okay, from positive to negative in that, and pointing in the d direction, and it has rho by 3 epsilon naught. But the question, oh sorry, double compensation, this would be plus and plus. The question is, what is the charge density on the surface? Okay, so since it's a small displacement, what is the charge density on the surface? So since d is along the k direction, so I can talk about the dr as a function of theta. Okay, that is, if I take any direction, here it is dr. Okay, at any which is, let's say this is theta, and so dr of theta, what is it? This will be the d dot n. Okay, and this is d dot, in this case n is r, so this is d cos theta. This is d cos theta. Okay, so yeah, so you can take it to be minus d dot, d is pointing in this direction, so it is d dot r is pointing in outside direction, so you can consider it to be minus d cos theta. Okay, so what is the charge density then? So charge density, so I can write down E in terms of rho by 3 epsilon naught. Okay, I can directly write it down. Of course, I have not. Okay, so I'll directly write it down. So sigma, I can write it down as rho d cos theta. Okay, so because that is what that small strip matters. So this I can write down as sigma naught cos theta. So the only identification that I do is that sigma naught is rho into that d small displacement that I have done. All right. So the solution that you have obtained is the charge density. Okay. The charge density is a by overlapping two spherical is sigma is equal to sigma naught cos theta. We get a constant inside, a constant electric field inside in the, okay, inside. Outside is, we require one or two tricks to obtain outside, but this result is of central importance. In both, we'll use it in conductors and in dielectrics for polarized bodies. Since E is E inside is equal to sigma naught by 3 epsilon naught minus k.